Hi class, in this presentation we're going to review the concepts in Chapter 14, which looks at algebraic thinking. Specifically, we're going to look at generalizations, patterns, and functions. Algebraic thinking begins in kindergarten as young students represent addition and subtraction either with objects, fingers, mental images, drawings, things of that nature. In middle school, students begin to study algebra in more abstract and symbolic ways, and they'll focus on understanding and using variables, expressions, and equations. While the Common Core state standards do not introduce functions until about 8th grade, functional thinking begins in the early grades as students consider situations that co-vary. And what do we mean by co-vary? Like, how does the price of t-shirts impact the number of sales? Those two items co-vary. Algebraic thinking is used to generalize arithmetic, to notice patterns that hold true in algorithms, and with properties to reason quantitatively. Researchers suggest that there are 3 strands of algebraic reasoning, and they're listed on the slide here. While algebra is a separate strand of the mathematics curriculum, it's also embedded in all the areas of mathematics, and we're going to focus on how it's embedded throughout all those areas today. On the last slide, you may have noticed that the first strand of algebra deals with structure in the number system. And we're going to look at 3 different ways to connect numbers to algebra. The first is through number combinations, and that begins in the early grades with decomposing numbers. For example, let's say you give your students the problem that's on the slide here, which states 7 birds have landed in your backyard, some landed on a tree, and some are at your feeder. How many birds might be in the tree and how many are at the feeder? Students can determine how many they want to say are at the feeder, for instance, and as soon as they do that, they would know how many are at the tree simply by calculating the difference. They could organize this in a table, and from the table they could generalize that the sum of the two, how many are in the tree and how many are at the feeder, will always be 7. The hundreds chart is another excellent tool to employ to aid students in generalizing relationships. And here's an example of an exercise that you could utilize to help students start understanding some of those different number structures. Suppose you ask the students to pick a number, any number that's on the numbers chart, and you ask them to move down 1 row and over 1. And then let's say you pose this question to the student. You say, what is the relationship between the original number and the new number? And then you might ask, what algebraic expression describes this move? Well, if you move down 1 row, you're adding 10 onto that number. And then if you move over 1, that's 11. So wherever you're at, the next number based on those moves will be 11 more. The students could start with arrows just to describe their moves down and over, and then they could start to substitute with symbols because they'll start to realize, oh, it doesn't matter where I'm at on that chart. If I move down 1 row and over 1, the result will always be 11 more. You notice that these 2 questions that I asked, the first one was just about the number, and then that second portion, what algebraic expression might describe this, asked the students to make a generalization. In this video, we're going to continue talking about connecting numbers in algebra. When studying an operation, students are often asked to explain how they solved a problem. As you listen to a student, you're going to want to ask questions like, okay, does this really show how you solved it? Because you really want them to be investigating their own understanding. This is really important when you're introducing students to algorithm. And an algorithm is basically any set of steps or sequence of steps that help you to obtain a certain result. And if you show students a number of problems with the same type of operation, they can start to establish the patterns and the rules that go with them. So for instance, on this slide, we're multiplying several similar fractions by the same whole number. And by investigating the products, the students might start to notice a trend or a pattern that exists when you change the denominators in these fractions. So for instance, 1/2 times 12 is 6. When we double that denominator to 4, 1/4 times 12 is 3. And then we double the 4 to an 8, 1/8 times 12 gives us 1/2. When we double the denominators, our products decrease in half. So students can start to establish some of these algorithms on their own. the greatest illustrations of structure and number systems are the properties. And we've talked a little bit about like the commutative and associative properties of addition and multiplication so far. I would encourage you to take a moment and pause this presentation so that you can look at the best ways to articulate what each of these properties mean, because that's really what you want to stress with students. It's not about can you memorize them and can you match a problem with the property that's used. No, the emphasis is on using and applying the properties. And you really want to help students to use them to generate equivalent expressions in order to solve problems efficiently and flexibly. That really is the most valuable part of all of the properties, being able to rewrite expressions into another equivalent form. And you want to stress to your students that these properties not only work for whole numbers, but for all real numbers, and that includes fractions and decimals. So really at the heart of what it means to do mathematics is the application of the properties of addition and multiplication. And you can use fun activities to help your students apply the properties. Here's an example of one. It's called 5 Ways to Zero. Let's suppose you have a set of playing cards, a deck of playing cards, and maybe you've given your students counters and number lines to use as visual aids. Let's say that the directions for this game entail drawing a card and asking the students to record 5 different ways to start with that number and to get to 0 using number sentences. Well, let's say you pull a 7. One example would be 7 minus 5 minus 2 equals 0. Another one would be 7 plus 3 minus 10 equals 0. Another one would be 7 minus 4 minus 3 equals 0. And you don't have to just use 3 numbers. The students could use as many as they want. But they're starting to actually apply some of the properties there. Another property that's really important for students to have a strong facility with is the distributive property. It's so important that they realize, like if they had the multiplication fact, 6 times 8, that they can break up one of those two numbers as a sum. Like they can take 6 and break it up into a 5 and a 1, and if they do 5 times 8 and 1 times 8 and add them together, that's the distributive property over addition. And that works for any multiplication problem. And then their ability to use that will help them to work more efficiently in problems that contain products or multiplication problems with unrecognizable or incompatible numbers. Okay, we're going to move on to that second strand of algebra, which is the recognition of patterns. Patterns are found in all areas of math, and learning to look for patterns and learning how to describe, translate, and extend them is part of thinking algebraically. There are several different types of repeating patterns, and repeating patterns are those that have a core in them that repeats. Repeating patterns are everywhere, and if you look at the screen here, you see several different examples of repeating patterns. Repeating patterns can be used to strengthen students' understanding of numbers. And it really helps to strengthen their understanding of multiples and division with remainders. How so? Well, for example, if you ask students to keep repeating the pattern A, B, C, A, B, C, A, B, C, you can ask them to predict what letter will be in the 12th spot. Now, they could write it all out and say, oh, that would be the 12th. And then you could ask them, okay, I don't want you to write anything out. Which one is going to be in the 16th? Well, they might start to notice that every third spot contains a C. Basically, anything that is a multiple of 3 will have a C. And what comes right after 15, which is a multiple of 3, is 16. So if C is in the 15th spot, A would have to be in the 16th spot. Now in 4th grade, you can connect this idea of remainders and repeating patterns to something that's much bigger. You could ask students to start with that repeating ABC pattern and ask them to predict the 100th term of the whole sequence. Well, if they realize that every third spot contains a C, that every multiple of 3 contains a C, and that 100 divided by 3 is really 3 remainder 1, then in the 99th spot is a C. So 1 more than that would make the 100th spot an A. Beginning in the primary grades and extending through the middle school years, students can explore patterns that involve a progression from step to step. When patterns involve a progression from step to step, they're called sequences, growing patterns, or even tessellations. That's what they're referred to in the artistic realm. And you want to start involving students in making generalizations regarding what the pattern will be at any point along the way. And they can do this in words, or they can do it in mathematical symbols and using operations. In the color tile illustration that's on the screen, you see you have both blue and purple tiles, but with respect to the quantity, you'll notice that the number of total tiles is always equal to 5 times the step number. And you want students to to think about things like that. In addition, they might notice that the number of purple is always equal to the step number, and the number of blue is equal to 4 times the step number. So there's a couple different patterns that are emerging in that one. If you look at the dot pattern, we're just going to talk about A for right now, but you want students to write out several until they can start to notice the pattern. And there's, again, a couple different patterns that emerge here. They might look at the step number and then the number of dots and see that they are adding 4, then 6, then 8, then 10. It's continuing to increase, but by a common difference. Or they might notice that to get any number of dots, they multiply that step number by the next one. So to get 2, which is the number of dots for the first drawing, they would do 1 times 2. To get the number of dots for the subsequent drawing, they would do 2 times 3. To get the number of dots for the next one, which is 12, they would do 3 times 4. So if a student recognizes that pattern, then they would know to get the number of dots for step 20, they would do 20 times 21, and that's going to give them 420. So they see a pattern that can occur regardless of the spot you are in the progression. You want students to think broad enough that they can describe what's going to happen for any nth case or any nth dot pattern. And it's important to also include fractions. And if you look at the last graphic on the slide, it says, if the list of fractions above continues in the same pattern, which term will be equal to 0.95? Believe it or not, but only 27% of 8th graders nationally responded to that fraction pattern correctly in a national test. I'm going to tell you the answer, but I want to challenge you to use some number sense and figure it out. The answer is the 19th, but see if you can figure it out on your own. Right now, it would probably be good to address the other word that's been in the title of the past couple slides, and that word is functions. A function is any mathematical relationship where an equation or a rule can be written to tell you how many output will be produced based on the number of input that you have, or if you're at a given step, how many objects will you have as a result. And you can produce a rule just like we did in the last couple of patterns whenever you have a function. Now there are different types of patterns or functions, and they are recursive, covariational, and correspondence. In a recursive pattern, the pattern changes from step to step in a predictable way, just like that dot pattern did in the previous slide. We saw that we were adding successive even numbers. So recursive relies on the previous steps to determine the next ones. For covariational, you're looking at how the two quantities vary in relation to one another. So if you're looking at the T pattern that's on the left top of your slide here, you notice that as you proceed from one step to the next, you continue to increase consistently the number of tiles by 3. And the last type of relationship is a correspondence relationship. If you look at this table, this is going to tell you how the number of input is related to or corresponds to the number of output. And tables are an excellent way to show how an input and output variable corresponds to one another. If you were looking at the previous slide and you were looking at the dot pattern in part A and you were asked this question, can you determine the correspondence relationship, the explicit rule, the the function rule for the dot pattern, if you sat and thought about it long enough, you may end up realizing that the number of dots equals, as we had mentioned, the step number that you're on times one more than that step number. So we could, in formula, say that D for dots equals N times N plus 1. What about for the dots that are in part C? So again, if you go back, you'll notice that all the dot patterns are in rectangles. But once you study that, you realize that the number of dots is equal to the step number that you're on squared plus the step number. So that would be N squared plus N. So you can establish rules for these functions, rules that show how these recursive or covariation or correspondence relationships exist using a mathematical formula. So what I'm doing on this slide is I'm producing a graph for the dot pattern in part A that was back on slide 8, and I'm producing a graph of the T pattern that was in slide 9. When we graph these, you notice that the dot pattern is curved. When you have something curved, it's exponential and it would form half of a parabola. But you notice that the T pattern is linear. It's a straight line, and quite frankly, it follows a specific formula, 3x plus 1. It's so good for students to be exposed to graphs early on and for them to make the connection between the table of values or the chart values that you've written out as a pattern emerges and then the graph. Even in elementary school, there are some important graph traits that you want your students to learn, like the difference between what it means to be discrete and continuous, and the difference between domain and range. You really want to have some discussion with your students in both of these graphs, if you should just have the graph represented by dots or if you should connect them. If you only have whole number inputs, which is what we had because we had just whole number dots and we had just so many squares that we were putting together in the T pattern, then you don't want to connect them, because connecting them would mean that you could have any fractional amount of dots or squares to form your T's, and that's just not the case. But if you could, and you would allow for fractional amounts, then you would want to connect them, and that would be the difference between continuous, connecting, and discrete, not connected. Also, just make sure you identify that domain is the technical word for your input values, which are also referred to as independent variables, and the range refers to your output or dependent variables. Linear functions are just a subset of functions, which can be linear or nonlinear. And again, it's really important for you just to keep thinking, okay, a function is just a pattern. It's a rule that relates an input to an output. And again, some of these rules can produce a line or something that's not a line. And we focus on linear functions because they're a major focal point in middle school mathematics. Linear functions all have a constant rate of change. It's the same from one point to the next, which is why it produces a line. In middle school, students need to be able to notice if situations are linear or not. So let's consider the example on the slide. It states, you are asked to build a rectangular pen with 24 yards of fence. Step 1. Write an equation to describe the relationship between the length and the width. And step 2, write an equation to describe the relationship between the area and the length. Okay, so let's talk about the length and the width of a rectangle. We know that in terms of perimeter, that perimeter of any rectangle is 2 times the length plus 2 times the width. And if we know that the perimeter is 24, that means we have 2 times the length plus 2 times the width must equal 24. Well, those are all divisible by 2, so we know that length plus width is 12. And that makes perfect sense. You can't have a length or a width that are more than or even equal to 12, because that produces a subsequent length or width that's equal to 0. So that wouldn't make sense. And you can even have the students model this in a table format, which is done on the screen. But once we have the perimeter formula and we know that length plus width equals 12, then you could rewrite either one of those variables in terms of the other. For instance, width would equal 12 minus length, or length would equal 12 minus width. Either of those are sufficient. How about area? Well, area of a rectangle is always length times width. And if you want to model an equation that's strictly in terms of length, you know that the width is 12 minus length. So you could sub that in for the width, and you have area is equal to length times 12 minus length. You could graph that on a calculator to see that it's not linear, and anytime a variable is squared, it's going to form a parabola if that's the highest power in the equation. How do I know that would be the highest power? Because if you have length times 12 minus length, the two halves are multiplied, so you'd have a squared term in there. So we see a linear pattern and we see an exponential pattern. You do see in the linear function that the width decreases by 1 unit with every unit increase in length. As I mentioned, all linear functions will have a constant rate of change, and this is called the slope, which you want your students to be familiar with. All linear functions can be modeled with a certain rule. That rule is y equals mx plus b, where m is the slope and b is your y-intercept, what the value of y would be when x is 0. And remember that slope simply signifies, it's your rate of change, but it signifies how much y increases or decreases with each 1 unit change in x. So you could have students start examining the slope between points 1, 3 and 2, 6, and as they look at it, they might say, okay, for each 1 unit change in x, I see y increasing by 3, so the slope is 3. And you would want to let students explore conceptually with several sets of points so that they could finally deduce the formula for slope, that it's the change of the y's divided by the change in the x's. Linear functions can also be proportional or non-proportional. What does proportional mean? To be proportional means that to find the output of the function, you just multiply the input by a certain consistent number. All the growing patterns that are on this slide are considered proportional. So again, you would just multiply whatever your step number is by a certain constant number to get the total number of figures, whether that's triangles or square tiles that are in each of your patterns. Non-proportional instead have a constant number that is added on. For instance, cost functions are always equal to your fixed cost plus your variable cost. Fixed cost stays the same no matter what. Maybe that's just the cost that you pay for rent each month, and it's always going to be a consistent $200. But variable cost is the cost per number of units that you produce, and that changes with the quantity of units. So if you're adding something on, that makes your model or your function non-proportional. One reason that students are unsuccessful in algebra is that they don't have a strong understanding of the symbols they're using. They really need to know that algebra symbols simply represent real situations and are useful tools in representing circumstances. The equal sign is one of the most important symbols in elementary arithmetic, algebra, and really in all of mathematics. Research over the past 40 years suggests that the equal sign is really poorly understood. So for this reason, the Common Core State Standards explicitly address developing an understanding of the equal sign as early as first grade. And they actually advocate that you introduce it through balance image, and that you always convey to your students that equal just means is the same as. That you're trying to show that one side of the balance is equal to the other side, that one expression is equal to the other side. So if you have the equation 5x plus 24 equals 54, and if you're thinking of it as a balance, students can reason that 5x must be 24 less than 54. Stressing is the same as is so important. In a study that was done fairly recently, researchers found that when students were given the problem 8 plus 4 equals what, a blank, plus 5, that only 10% of the students in grades 1 through 6 got the problem correct. Why? Because they are simply thinking of 8 plus 4 equals what, and they were plugging in a 12, not realizing that the whole left side of the expression needed to equal the whole right side of the expression. And students get used to be given equations that are very simplistic, that say 8 plus 4 equals what, and the question mark is always isolated instead of having the question mark with something else added or subtracted to it. And it's so important because that way students get a more well-rounded, full understanding of what the equal sign means, that it means is the same as. Having students write several different sums that are equal would help to convey the meaning of the equal sign, like saying, okay, 72, show me 3 different ways that you can express a sum that equals 72. So maybe students showing 60 plus 12 equals 70 plus 2 equals 50 plus 22 will reinforce the balance aspect, the is the same as aspect for students. I think that this activity is terrific for emphasizing the concept of the equal sign. In this activity, which can be found in your textbook, it's labeled as 14.15, you are asked to introduce to your students the concepts of true and false statements. So you might want to give them an example of a true statement, like 3 is equal to 1 plus 2, and then an example of a false statement, 10 plus 1 is equal to 10. And then you might want to put on the board several different true and false statements and have students work in pairs to determine which are true and which are false. This helps to really get across the emphasis of the equal sign. You do want to make sure that you don't make these problems too difficult in the early elementary years, but you do want to include a variety where you don't have just one operation exclusively on one side equal to just a whole number, but that you try to have operations included on both sides so students continue to reinforce that idea that the equal sign is the same as the expression is the same as. As students start to become exposed to equations in their elementary education, they're going to work through a series of progressive views of what equations are and what they represent and how to work with them. The first view is called the operational view. In this view, students see the equal sign as meaning to do something. So if they see 6 plus 7, they think, I need to do something with it. I'll add it. That's the most elementary view. The next phase, as they're learning more and becoming more accustomed to equations, is the relational computational view. In this view, the equal sign symbolizes a relationship between two calculations, so they see the need to calculate. So when they're given the equation 7 plus n equals 6 plus 9, they automatically calculate what 6 plus 9 is and see that they're trying to produce a number to equal 15 when added to 7, and so they'll come up with 8. The last view is the most sophisticated. It's the relational structural, and it's really based on a strong sense of numeric relationships. So when students see that 7 plus n equals 6 plus 9, they automatically think, well, 7 is 1 more than 6, which is on the other side, so that means my n should be 1 less than 9. So their sense of numeracy is much stronger, and they're starting to connect that with the unknowns or the variables in the equations. Just like equations can be viewed in various progressional ways, so can the variables within them. They can be interpreted in different ways. Variables are first mentioned in grade 6 as part of the Common Core State Standards, and variables can be used to represent a unique unknown quantity or a quantity that varies. Unfortunately, it's the former, that it's a unique unknown quantity, that is mostly used. But a variable can represent multiple, even infinite values, and we'll talk about that in just a bit. When you start working with variables, you'll want to do so with easy contextualized problems. In addition, you can start to visually introduce systems of equations through the balance technique, which you see on the slide here. And you're going to want to look at all these different ways that you can have students start to think about various changing items in the relationship between those items that are there. I think the balance makes for a very fun and challenging mathematical experience in the area of equations for students. So what does it mean to present your students with variables that represent quantities that vary? Well, let's say that at Christmas the Salvation Army supplies 3 presents per child, and they want you, or you're asked to write an expression for total presents. Well, we don't know what the total presents are, but we can say that P, which represents presents, will equal 3 times C, letting C equal total children. So they can both vary there, and it's important for students to realize that you can set up equations with multiple unknowns, but they can show that a certain relationship does indeed exist. In middle school, you can also present the varying quantity idea with a problem like this. If you have $10 to spend on $2 granola bars and $1 fruit rolls, how many ways can you spend all your money without receiving change? Well, there are several different ways, and students could use a table to organize data for a problem like this. It's vitally important that you also include fractions and decimals in problems like this, because those are quantities that students really struggle with, and the more exposure they have to them, the more comfortable they're going to feel working with them. Modeling with a balance is an excellent way to help students make the connection between equivalent computations with just numbers, no variables first, which is modeled on the left side of the slide here, and then determining what unknown values should be in an algebraic expression, which is modeled on the right side. I'd like you to take some time and study the commentary that's written out here to see how you as a teacher would model these problems explicitly for your students. If you need to make it larger, it's also on page 325 of your text. And there is some balance paper that you could use that's part of the e-resources that go with the textbook, so you could print this out for your students so they have a visual aid and they could follow along and take notes. And I think that's important when you're teaching equations, because the writing of the notes also leads to muscle memory, and the students start to make a mind-to-hand connection for what the next step should be. Throughout this presentation, as I've talked about equations and functions, patterns, we've also mentioned the word modeling. Well, modeling in mathematics is simply one of the 8 standards for mathematical practice in the Common Core State Standards, and a model is simply an equation. It's a rule that relates input to output. And creating equations to describe a situation is an extremely important skill, and students need multiple opportunities to translate situations into equations where the goal is a mathematical model, where the goal is to produce a rule that no matter the number of input, you could determine the output. No matter the independent variable, you could determine, or the dependent variable, the result. So that's exactly the goal of these 2 problems that are on the screen. And these would be great for students that are in upper junior high. And what I'd like you to do is just pause this, take some time and try them, and we'll review the answers to both of them during class next week.